First of all, thank you for coming. This speak will try to, the main aim of this speak is just to show an overview of what cellular networks are, how they evolved a long time, and basically which are the research topics, the research fields that are going to be, let's say, play a key role in the future. Yeah. So basically, the structure of the presentation will not be probably as usual, because I will try to show, first of all, just to be aware of which is the current situation. So it's not difficult to realize that cellular networks are playing an important role in our daily lives. It's not difficult to go to the metro station and see everybody just watching the screen. Watching the screen, people working on the cafe, some people doing some selfies, etc. So actually, cellular networks are playing an important role in ICT society. However, it was not always the same. I mean, not so many years ago, okay, this peak is a little bit old, but not so many years ago, things were completely different. I mean, when you went to the train station, when you went to the bus, etc., nobody was watching a screen and was working with a mobile phone, a handset. So basically, I would like to know how fast this happened. And I think in order to explain this, there's an example which is usually used in some presentations, which is it's worth looking at it. And here's this one. Just to give an example how fast things happened. On the left-hand side, we have the election of the Pope Benedict in 2005. On the right-hand side, we have the election of Pope Francis in 2013. There's something which is, the picture is taken more or less in the same place, but there's something which is pretty different. In 2013, a lot of screens, a lot of people just recording, just taking a picture of the moment. In 8 years before, this is something that was not happening. So how these things become so fast, happen so fast? This is something that probably it has to do with how things evolved. So I think it's important before explaining what is going to happen in the future with this kind of technologies, I think it's interesting to know how everything started, how we reached to this point, how some decisions that were taken in the past affect our nowadays communications, cellular communications. So basically, I would like to show, let's say, a chart which is usually used as well, in order to show which is the expected traffic in the future. As you can see here, I mean, the growth of the traffic is ever increasing. It's not going to stop. So cellular networks must be able to meet this demand. Apart from that, this chart is from Ericsson. Apart from that, it's worth looking at which kind of devices are the source of this traffic. And as you can see, smart devices, smartphones, are the ones which are going to generate most of this traffic. After that, laptops, etc., and note how marginal will be the voice traffic. So basically, we are heading for a society demanding a lot of data, great amount of data, and our cellular networks must be able to meet this demand. So according to that, and based on these numbers, for instance, that the annual growth for the last years has been 45% annual, and for instance, from 2014 to 2020, there is the expectation that the traffic will grow tenfold. So this is something that must be taken into account. And in order to meet the demand in the future, we have to take some decisions, to make some decisions right now. And this is what actually the research community is doing at the moment. So let's try to see how everything started. Yeah, mankind always wanted to have distant connectivity, distant communications. In fact, smoke signs, telegraphs, light signs, everything is wireless, is distant communication. But the thing is that we want every time more efficient systems and more complex systems. And this is why, for instance, smoke signs, which is obvious, telegraphs, and light signs, for instance. But there's also something which is interesting and which is important. It's the key point of the communications, and it's the mobility. Being able to manage the mobility of the users. So basically, and taking into account that actual current cellular networks are based on wireless communications, I would like just to stress, just to point out main challenges of wireless communications, any kind of wireless communications. And wireless communications are basically characterized by sharing the medium. We are sharing the medium. It's not the same as when we have a copper or a fiber optic, and we have that medium dedicated for us. We have to share this. And if we transmit in the medium, in the air interface, in the medium, what we have is that we limit the capacity because we interfere others. Apart from that, the mobility. It's obvious, it's very clear that when you have a fixed connection, you needn't manage the mobility. You are fixed, you are there, you are static. However, when you are wirelessly connected, you have to cope with mobility management. One of the, let's say, main issues for cellular networks. So basically, the principles of any wireless communication system should be, first of all, trying to find orthogonality. And when I say orthogonality, which is a mathematical concept, but it's not that difficult to understand, it means that we have to find the way to divide or just to distinguish the different users using the same medium. And this orthogonality goes from time, it means not transmitting simultaneously, this requires synchronization. Frequency, it means multiplexing signals into different frequencies. Space, obviously, transmitting somewhere and not transmitting simultaneously in that place. Code, it means using orthogonal codes in order to orthogonalize the signals, etc. I mean, this orthogonality is one of the main issues for any engineer trying to design a network. He wants to achieve as much orthogonality as possible between different users. If we manage to do that, we will be able to decode the signals of each user in particular. And basically, this is for the shared medium. For the mobility management, the process called handover is the key process. Handover is basically defined as the process where a user connected to a particular node, let's say a base station, due to the movement of the user, has to reconnect to another base station while the session is ongoing. Handover. So, having this in mind, these are the main challenges that, from the very beginning, engineers, different network designers, had to address. Yeah? So, let's start with, let's say, the first mobile communication systems. First mobile communication systems were in the early 80s. Yeah? As you may see, in different countries, for instance, in the USA, in the UK, Japan, etc. Also in Nordic countries, Finland, Sweden, Denmark, Norway, and Iceland, which were the pioneer countries in developing this kind of systems. All of them try to develop different standards. They were just addressing something new. I mean, they didn't have much requirements about capacity, demand, these kind of things. No, they just wanted to show that it was possible, and actually there was a market for that at the beginning, just for the, let's say, for the public sector. There was a market, and the technology was mature enough in order to develop this kind of systems. However, okay, these systems were characterized by some issues. They were analog. This is something that, at this point, for us, it's something which is amazing, but initially, they were analog. Imagine, for instance, like, basically they were They were based on FDMA, frequency division multiple access. Just to say something, for instance, it was like radio, AM, FM radio. So it was more or less the same. Yeah. And the radius of the cells, so the coverage area of each cell was huge. Let's say about 30, 40 kilometers. Yeah. So these were the characteristics of these first attempts in order to build these networks. However, as obviously, if we compare it with what we have today, we can realize easily that there are some limitations. Which are those limitations? Okay, there was a limitation in capacity, obviously. Why? Because basically, what they did is that they assign, as we do nowadays with every radio station, they assign a frequency, a band, a particular band for each user. This limits quite a lot the number of users. This limits the capacity. Apart from that, as they were analog, obviously the efficiency in the usage of the spectrum was limited. So the capacity was limited. If the capacity was supposed to be increased, a radical change should happen. So apart from that, there was another problem, which right now perhaps it looks like a strange thing, but at that time it was something very usual. There was not a global standard. Note, for instance, here I listed three different standards, but take into account that these are not the only ones. We can go, for instance, for 5 or 6. So basically, what we have here, having so many standards, different standards for the same with the same objective, means that the roaming, this concept which is, let's say, so fashioned right now, the roaming, the capacity, the ability to get connected in every single country with the same handset, this is something that it was almost impossible. Every time you went with a mobile phone of one of these systems to another system with another system, you were not able to roam, you were not able to get connected. So this was a practical limitation, and this is one of the things that the research community actually realized from the very from the early beginning, from the very beginning of the network. So what they did, they went for a second generation. The second generation here in Europe was GSM. It's actually, this is a success story, because actually when you take your handset, you will realize that all of your handsets are implementing GSM. They are GSM handsets, they are GSM devices still now, and it was designed and it was launched in the 90s, early 90s. So they have been active for more than 20 years. And right now, if you have a voice call, probably you are using GSM. So basically it was a success. But unfortunately, this time it was not the only standard in the world. There were other options, like for instance digital amps or IS-95, also called CDMA-1. These standards were mainly designed in the States, in USA, and they were based in different technologies. Yeah, you can tell it from the name CDMA. In fact, some experts admit that probably technologically the American standards were much better than GSM, were more efficient, were better actually, and history supports that. Because third generation networks were more based on these concepts, the concept from the American standards rather than from the European one. But okay, why GSM became the most prominent network, cellular network? Because of the market. Because as it was simpler, it was technologically simpler, let's say. It was launched before in the market. It was cheaper. So basically, sometimes doing or just designing the best system not necessarily means that this will be the de facto, the standard de facto. Yeah? So let's say GSM was a great success. How did they improve all these limitations that we saw in the previous slide? Basically, they went from analog world to the digital. In fact, this should not be good by itself. The good thing of the digital communications is that they are more efficient. There are much more modulation schemes that make the communication much more efficient. So, but when I say that the communication is much more efficient, I mean that more bits per second can be transmitted over a unit of spectrum, a hertz, for instance. Yeah. So this is what they did. And they did something interesting, which was, in the previous generation, everything was, let's say, based on FDMA. So users were divided into different frequencies. Here they changed the concept, and they used as well this. So they just design channels, allocate channels in different frequencies. But as they had digital communications, which is much easier to multiplex in time, they decided to multiplex or to divide these frequency carriers into time. And they designed this divided in slots. In fact, in GSM, for each frequency channel, you can multiplex 8 users. Yeah? Note that simply by doing this, and thanks to digital world, and thanks to better efficiency, what we have is that we have a more efficient system, and so we have a higher capacity. However, it was not exactly designed for everything. We have to take into account, we have to bear in mind when it was designed. It was designed in the early 90s. So basically, it was voice-oriented. It was oriented on circuit switch network, as a circuit switch network. What does this mean? It means that when a user establishes a call, let's say a stream, wherever, the network reserves a whole circuit for it, for this user. So basically, if there is a user on the phone, it means that that resource cannot be used by another user. Yeah? So this is why with GSM, users paid for the time they were connected. Because while they were connected to the network, another user could not get connected to the network. So this is why they pay for the time. This is something that we don't do right now. Yeah? And however, it's also true, it was digital, that based on the capacities, on the ability of the network itself, it was possible to transmit some data. But note that the data was circuit switch based. So they paid for the time it took them to transmit this data. But the rates were, I mean, ridiculous compared to what we have right now. 9 kilobits per second, 14 kilobits per second. This is nothing today. At that time, it was amazing. So this is this is the network they designed. But there was something which was at the beginning was, let's say, kind of lateral, and which was really a success. The short message service, SMS. SMS was not designed in the first releases of the standard. It was something that came afterwards. It was an additional service which was added to the standard in order to transmit in an easy way some small packets, some data. And this is why the number of characters that could be transmitted through the SMS service were, let's say, were short. I mean, the messages were short. Yeah. Why were they short? Basically, because they were transmitted not as data, not as voice. They were transmitted as control information. They were transmitted through control channels. So in fact, what they were trying, network operators were trying to do was, they had some control channels usually oversized, let's say, without having the, I mean, they had some spare capacity there, but in the control plane. And they said, what can we do in order to get something from there? And this is what they decided. They decided to include that. And actually, it was the success. It was one of the key of the enablers of the following generations. People got used to send data, text data, but data in the end. Yeah. So when they had this, they decided, and when I say they decided, I mean the research community, I mean the standard. In that time, at that time, ETSI, yeah, the European agency, they decided to include some new features to the system. And this is what they called GPRS. GPRS was the first attempt in a network like that to build a packet switch system. When I say a packet switch system, I mean, for any engineer, they know that packets are transmitted, no need to reserve different circuits, but in the end, for the user, for the consumer, it means that they paid for the data they sent. This was something new. But it's also true, look, for instance, we went from, let's say, 14 kilobits per second to 170. Right now, it's less, I mean, it's nothing. But take into account that it was a tenfold growth increase. So it was not that bad. And how did they do that? In order to, I mean, with the network they had. Because actually what they didn't want to do was changing the network they deployed. They did something. They just said, okay, instead of these 8 slots, time slots, instead of allocating 1 slot per user, we could allocate more than 1 slot per user. So if we decide, imagine that we are able to transmit, for instance, 14 kilobits per second in GSM. When you go to the to GPRS, let's imagine if you, instead of allocating a single slot, you allocate 2 of them, you get the transmission rate doubled. If you include a 3rd slot, you get 3 times the previous transmission rate. So basically, GPRS was designed in that way. It's also true that this is the air interface. So in the network part, there were some new nodes in order to manage what was called this packet switch system. Yeah, because it was a little bit different. But what they did was just enhance GSM. If you realize, if you look at your handset, you will realize that, for instance, when coverage is really bad, you have, let's say, those bars indicating the coverage you have. Sometimes, when it's a little bit better, and when you try to get connected, but coverage is not really good, you get a G. It means that your handset is working with GPRS. So this is something which is actually used. And then, however, demand started increasing. So people were asking for more demand, for more capacity. And what did they do? Just modify the standard again, just try to enhance the standard. And they designed, or they included the features for edge. And once again, when you look at your handset and you realize that next to the bars of the coverage you have an E, it means your handset is working with edge. So basically, the mobile phone tries to work with the better system available. And note, here we increased a little bit the rates. How did they do that? Basically, what they did is an adaptive modulation encoding scheme. What they did is, okay, we have GPRS, we have GSM, but if we have a good channel, if we have a good quality channel, what we can do is that we can increase the order of the modulation. So basically, we can transmit, we make the system more efficient, we can transmit more bits per second for a unit of spectrum. Yeah? So basically, this is what they did. Do you remember when advertisements about 3G came out? Do you remember? I mean, it was not long ago. What happened there? Note, in the society, what happened at the time is that broadband connections, I mean fixed, ADSL, fiber optics perhaps, in some places, they started to be usual. people was used to get connected through broadband connections, broadband access technologies. So something that happened in the fixed world, let's say, in the world of the fixed connections, was translated into the cellular networks. People were asking something similar to what they had at home on their mobile phone. And this is the reason why edge was also not enough in order to meet the demand. Which were the the limitations? The flexibility was not that much. Why? Because what we have with edge is that we adapt to the channel conditions, we adapt the number of slots that we allocate to each user, but in the end, the number of services, of new services, web browsing, FTP, etc., the number of new services and the characteristics of those services were changing and were more diverse. So basically, the structure of edge, GPRS, GSM, which were initially designed, the whole structure of the network was initially designed for voice, for circuit switch, although afterwards there were some, let's say, modifications in order to have good or acceptable data communications. Oops. Let me. Okay. So it was not enough, so something had to be done. And this is how the idea of 3G came out. What about 3G? 3G meant a breakthrough in technology. As you may remember, second generation networks were based on FDMA, TDMA, etc. Here, they used another concept, which was code division multiple access. It means that signals of each user, instead of being, let's say, divided or split it up thanks to the time division or frequency division, there was another dimension to take advantage of, which was CDMA. Signals were multiplied with orthogonals or pseudo-orthogonal codes, and they were just transmitted into the air interface. What would, let's say, which is the concept of this kind of transmission, of the CDMA, this kind of access? Basically, these sequences, these orthogonal sequences, are sets of ones and minus one, let's say, sequences. Note that if in the transmission you multiply the signal by this, and in the reception you multiply the signal by this, the same, which would be this case, there's no effect on the received signal. What happens with the other signals? With the other signals, they use something interesting, orthogonality. What's orthogonality? Orthogonality means that this expression, when you integrate the multiplication of the two sequences, this is zero. In a few words, it means that when using code division multiple access, we were able to get the information of a single user, even though it was transmitting simultaneously over the same frequency with other users. So this was one of the main new concepts of this third generation. And if you remember, I told you that for the second generation, in the USA, there were some, let's say, some standards that actually were working with CDMA. Okay, this is the proof that those standards were probably much better than GSM. But what happened? Initially, third generation, let's say, started as an initiative, as an effort, a global effort, to have a global, this time for sure, a global standard. a standard that could be used all over the world. Did they manage to do it? Not at all. Why? Because there were some countries, the US, Japan, for instance, etc., where GSM was not deployed or was, let's say, marginal. And some others where GSM was, let's say, the prominent system. So basically, it has an impact on the network, on how the network is. So 3GPP, which was, let's say, the standard organization in charge of this development, was divided into two different standards. 3GPP2 for those countries or those systems evolving from the American standards, and 3GPP for those standards, for those countries or those systems evolving from GSM. Yep. And note that here, thanks to this new technology or the technology they used, they started reaching much better transmission rates, about 2 megabits per second. This is something that we experience in our mobile phones, yeah, right now. However, as always, demand keeps growing. Demand keeps growing, and it means that we have to do new things. We have to improve, enhance our systems in order to meet that demand. What did they do? They design what is called HSPA. When you, for instance, when you look at your mobile phone and you see an H, it means that you are implementing, you are using this system. This system basically is exactly the same as the first one, as the third generation system. But there were some features, some new features that were interesting. Some, let's say, they started sharing some channels without contention. Yeah, they included new modulations. They just designed some automatic repeat request algorithms to correct the errors in a faster way. So basically, what they achieved was more or less 7.52 in the uplink and 14 megabits per second in the downlink. And obviously, they kept enhancing the system, and they just included in the standard some new features, HSPA Plus, that included the MIMO concept. I will explain later on a little bit, just a few words about the MIMO concept. But the important thing is that the evolution kept going. Yeah. However, once again, capacity was not enough. And we go to fourth generation. Fourth generation is what we have right now. I mean, in most of the new mobile phones. Yeah. For the 4G, everything changed again. We changed how we access the medium with a new access, OFDMA. OFDMA basically divided the spectrum into narrow band carriers. These narrow band carriers were divided into time, and the multiplexing of time and subcarriers was the result of this. Okay, the reason is let's say, it's probably just for engineers in order to understand why this works better. But the thing is that with this, they achieved much better data rates. And in fact, as I told you, orthogonal frequency multiple access, this is the key point. MIMO and cooperative multipoint was another feature, and networks were this time all IP. And something which is very important. Let's say this was the first real standard accepted worldwide. I mean, the global standard. This is the global standard. This works everywhere. Yeah. So just few words about MIMO, which is important for LTE, and you will see that it's important in the future. MIMO is including more than one antenna in the reception and in the transmission. With this, we have different gains. First of all, spatial gain. Note, we have different paths from one antenna to the other antennas. We have different paths. So based on that, when the channel is VAT in one of the paths, the receiver could select other paths. So basically, we are gaining in spatial diversity by having different antennas located apart, not together. Yeah. There's another effect, which was the array gain. The array gain is basically that right now, if you don't have MIMO, base stations and users, but basically base stations, transmit to all directions. Yeah? With this, with the arrays, so including more than one antenna in the transmitter, for instance, what we have is that we are able to direct our transmission to a particular location. So we are not transmitting everywhere, but we are transmitting where we want to transmit. What we do with that, what we get is that we minimize interference. We improve the received signal. Yeah? And why this MU means multi-user MIMO? It means that simultaneously we can transmit to different users with different beams in different locations. And with this is pretty obvious that we have a gain in capacity. But there's another, let's say another gain, which is the spatial multiplexing gain. This means that even having a single user, we are able to send from each antenna different streams, different data. By doing that, we are multiplying the data that we are transmitting simultaneously. So basically, the result of this is that we increase the capacity, the transmitted rate. Yeah? So this is an important aspect for current communications and definitely for future communications, this MIMO concept. And now, I mean, 4G, this is what we are deploying. I mean the network operators. This is what they are deploying. But what about 5G? As you may know, 5G is the objective, is the goal of the research community. All the research community, all the academia and industry are focused on this. And actually, first experiences of 5G networks, initial experiences, will happen in Tokyo for I think it's the Olympic Games, and in Korea for the Winter Olympic Games, which are, I don't know, in the near future, I mean in few years. So they will be the first ones to experience with a 5G network. Obviously, it will be initial. It will be initial. Not all the futures which are envisaged or expected for 5G networks will be implemented, but it will be a first experience. So it will be nice to look at those events, sport events, in order to see how it works, which is the capacity which is achieved. So I think we should keep an eye on that. So basically, which are, let's say, according to the 5G infrastructure public-private partnership, yeah, which is a consortium, let's say, of all of the industry in the sector funded by European Union. Basically, which are the goals? Ubiquitous connectivity. So basically, we want to have connectivity everywhere. We want to be connected all the time, everywhere. Always on. We want to be always on. And there's an interesting concept regarding the connectivity, which is quality of experience. For network operators, they do not care much about the transmission rate. They care about the experience of the user. So, the experience of the user means that if I'm watching a video on my tablet, for instance, it's not important the transmission rate I receive in order to see the video. The important thing is the latency, for instance, the delay. Wherever it impacts on the perception I have of the service, in this case, of the video service. So, right now, all network operators are focusing on deliver proper quality of experience. And it has some problems, as you may know, etc. The other interesting thing is that, obviously, if we want to design a 5G network, so a network for the future, we have to increase the capacity. And according to this entity, where I mean, a consortium of all industry in Europe, they understand that in the future we should get this amount, 10 terabits per second per square kilometer. This is amazing compared to what we have right now. Yeah. So notice it's multiplying by 1,000 times what we have at the moment. Yeah. So I will try to explain more or less which are the key enablers in order to get this. And at the same time, they expect a huge number of connected devices. At the moment, we assume that devices connected to the network are our handsets, our laptops, our tablets, this kind, so human-type communications. In the future, this will be part of the traffic, but the other part of the traffic, and increasing every day, will be the machine-type communications. It means that sensors connected to the network, cameras, resilient cameras connected to the network, etc., etc. Devices over the body for e-health, for instance, everything connected to the network. So we will have to, or the network will have to be able to manage this huge amount of devices. At the same time, we will have to reduce the energy consumption. At the moment, afterwards I will show you some numbers, but the energy consumption is one of the key factors for obviously environment reasons, but at the same time for economic reasons. Yeah, because the network operator has to pay for the energy. Yeah, very high peak data rate. So it means that apart from the aggregate data, we need, for instance, in particular places, in particular situations, very high traffic data rate for a particular user. Yeah, 10 gigabit per second, for instance. Reduce the latency for different new services, and obviously decrease the operational expenditure. So basically, decrease the cost for the operators to deploy this network. Yeah. So if we go a little bit into this, you can see that also in this consortium they elaborated this chart. In this chart, what they show is here in dark blue you have the situation of the 4G, our network, and here you have mobile data volume, peak data rate, mobility, number of devices, energy efficiency, service deployment time, reliability, end-to-end latency. And what we see is that these are the objectives for the 5G, and this distance is how far we are from 4G to 5G in order to get these numbers. Yeah? So as you can see, this is something which is challenging for sure, and this is why all the research community is focused on that, is aimed to get or to work together, to do a joint effort, because otherwise it will not be met. It will not be met. Sorry. So based on that, and just in order to explain what the aggregate data is, if we have this situation, the aggregate data, so what we said, for instance, the terabit per second per square kilometer, means the aggregation of all data rates should be that value. If we talk about the peak rate, for instance, is a user with a very good quality signal should have a minimum peak data rate. Yeah. Cellular rate, this is important. This is important in terms of quality of experience. If we want to get quality of experience, we should not care if we are close to the base station or far from it. So we want to have at least a minimum cellular rate, so a rate far from the base station, in order to guarantee this quality of experience. In this case, the farthest one would be this one, the fifth one. And obviously, the network, the whole network, should focus and should optimize itself according to new KPIs instead of quality of service, delay, etc., quality of experience and mobility, the management of the mobility. Yeah. So the way to achieve this connectivity and this capacity, this huge increase, is in principle clear. We should improve the performance of the air interface. We should as well improve the spectrum 10 times. And we should increase the number of base stations. So we should densify the radio access network. With this, if we get an increase of 10 times, 10 times, and 10 times, in the end, we get the 1,000 times capacity, the increase of 1,000 times in the capacity. Yeah? So, if we go a little bit into the different details, the spectral and these three issues, we have the spectral efficiency, measured in bits per second per hertz, and how they are going to meet this increase, this tenfold increase. Basically, they have two options, let's say, or two options are the most important ones. First of all, massive MIMO. If you remember the concept of MIMO that I briefly described a few slides before, here they are considering the inclusion of not 2, not 4, not 8 antennas in a device or in a base station particularly, but hundreds or thousands of antennas. So it means that each node, what we see on the rooftop will be like 100 or 1,000 antennas, small antennas, but antennas as well itself. So this is an option, and another option is the exploitation of the device-to-device communication. It means, okay, if we want to improve the spectrum capacity, and if we have some users around, and we want to communicate with them, perhaps it's not necessary to get connected through the E node B and do it directly. So if we go into the two concepts, for the massive MIMO, there are some advantages, which are an energy reduction. We are much more efficient. We are transmitting where we want. We are very, very efficient. Simultaneous scheduling of several users, what I explained. The more antennas you have, the more users you can simultaneously select. Yeah? So basically, we increase the number of users, simultaneous users that you are serving. Obviously, every time we increase the number of users, we multiply the capacity. And obviously, the capacity of being very directive. So we are able to, for instance, we are able to transmit to a user which is located there, and a few degrees next to this user, interference will be 0. Yeah? So this is important. But obviously, there are some challenges that are being addressed by the community, the research community, which are, for instance, channel state information acquisition. Basically, if we want to do that, we have to get information, we have to sense the medium from all the antennas. There's no problem when you have 2, 4, 8 antennas, but when you have 100, when you have 1,000, this is something which is complex. And this is one of the things that is, let's say, putting into troubles the guys working on this. And another thing is that obviously you have a huge amount of parameters and some degrees of freedom. So you have the possibility of let's say, of using more beams, being more directive, wasting more energy, consuming. So there are some management degrees of freedom that must be, if you want to be optimal, you have to address. So, and the other aspect was device-to-device. Basically, up to now, device-to-device communications are designed for proximity services, what I explained 2 slides ago, 2 slides before. Basically, what they say is, instead, if we want to connect this user with this user, if we want to, instead of getting connected through the E node B, through the base station, which is what would happen, we can just operate in a direct manner. Yeah? We can communicate with each other without the assistance, okay, with the assistance, but without using the small cell or let's say, the base station. This is something that is pretty limited. Why? Because in order to be able to do that, you have to have 2 users wanting to connect, to communicate with each other, and a good quality channel here. So this is pretty limited, and probably it's more likely to happen in some, let's say, in some Okay, in some situations of, for instance, an earthquake, etc., yeah? Which is the possibility? And actually, we're working on in the group with this. The other possibility is just trying to clusterize the users. So users get connected among them, and then they get connected to the cell. So basically, what we have is a user, which works as a cluster head, and then it connects with the rest of the users, and then forwards the information to the base station. With this, we can save energy, or at least spectrum, and we can improve the capacity. However, there are some challenges for this proposal. The detection of the users is not easy. It must be assisted by the base station. Another possibility, mobility management and session continuity. Okay, the mobility, it's not easy because if these users are moving around, it's not that easy to keep the cluster updated. Another point is the energy consumption, how the energy consumption is distributed among the different users. And finally, which are the incentives for the users to cooperate. Yeah. So after that, there was the second point, which was spectrum. We wanted to increase the spectrum by, let's say, 10 times. Here, I included a slide with the current situation of the spectrum. Basically, you have here, let's say, the four network operators. There are other network operators, but they are virtual, so they are using their network, yeah, and the spectrum bands they use for each of the systems that I told you. For instance, as you see, all of them have deployed GSM, UMTS, LTE, etc. Yeah, but notice that the bands where they are deployed are restricted. I mean, 900 megahertz, 1.8 gigahertz. 2 point something for the UMTS and 2.6 gigahertz for the LTE. Note that these bands are pretty limited, and they are limited because this is the international community who is in charge of allocating these spectrum bands for the different systems. So if we want to if we want to increase the spectrum availability, we have to go to other bands. For instance, for LTE, for G, what we have is that basically in Spain, each operator has 20 megahertz bandwidth, in some cases 40. So note that this amount, in these frequencies I mean, this amount of bandwidth is pretty limited. Note something that, this is regarding, for instance, when the TV system changed, I mean, they changed the frequencies where they were broadcasted. Actually, it was to allocate more spectrum to these systems, because otherwise, LTE systems will not be able to work. So, if we go to the new bands, we have different options.
Okay.
Yeah?
When you say about the tenfold increase in spectrum, you only mean to increase the spectrum or also to reutilize?
Yeah, I have another slide after this talking about reutilization. But the concept is having 10 times more spectrum. I mean, you need more hertz, no matter how you get them. So we could include the two concepts. I will explain it. I have a slide for that. Yeah. So basically, if we want to find new bands, the research community has put the focus on frequencies, spectrum below 6 gigahertz and from 6 gigahertz to 300 gigahertz. These are, let's say, very high frequencies. Yeah. Why 6 gigahertz? Why this limit? Okay, I will explain. The available bands, because I mean there are many services. Yeah? So the available bands in 6 gigahertz, not used by radio stations, but television, TV stations, etc., are not enough to meet the expected demands. So basically, the research community is focusing on bands above 6 gigahertz, where bandwidth could be around 500 megahertz or 1 gigahertz. Note that right now in Spain, for LTE, operators have not more than 40 megahertz. So we are looking for bands to allocate more than 10 times the available spectrum bands that we have right now. Yeah. One interesting thing is that this division, I mean below 6 gigahertz and above 6 gigahertz, so I mean this threshold, has some reasons. Actually, in the World Radio Conference, there's a World Radio Conference every 4 years where all countries decide aspects related to radio communications in the ITU. It's organized by the ITU, basically. So this year, in 2015, there was in the agenda, it was scheduled to decide about frequencies below 6 gigahertz. This is why this is the threshold in order to see what we do with 6 gigahertz. What different network operators, which was something that was not easy, they managed to do this year was to include in the agenda for 2019 the allocation, or at least the discussion, of frequencies above 6 gigahertz. This is something important because in 4 years' time, probably the demand will be huge and we will need this spectrum. So basically, it was important for all the industry, and this is why they pressed this year and why they achieved the schedule of these bands in the agenda of World Radio Communication Conference, World Radio Conference, to include these bands. Yeah? And let's focus on this because here is where we have the required spectrum. These bands are called millimeter waves. These are the future for the cellular networks, for sure. We will get the spectrum there. As I told you, it has been included in World Radio Conference 2019, so it will be discussed. And there are, let's say, some problems, some challenges in order to address before using them in commercial systems, which is, first of all, we need to accurately design the channels. Frequencies or signals in different frequencies behave in a completely different way. The behavior of the signal at 2 gigahertz or 50 gigahertz are completely different. So in order to deploy, to implement, to use these frequencies, we have first of all to study. There are some pioneering groups in like the University of New York and the University of Texas Austin, which are pioneering in modeling these channels. And there are some accurate models at the moment that can be used for the research. The other characteristic is that severe path loss. The path loss is huge, so the signal received from the base stations will be low. In order to address this is why this kind or this spectrum will be allocated to small cells, some cells close to the users, because otherwise the capacity, the signal would be extremely low. And finally, there's an important point that these channels are characterized by 3 states, something that didn't happen in the frequencies we are using. And it is line of sight, so there's a line of sight between the antenna and the user, the base station and the user. No line of sight, there's no line of sight between the base station and the user, so the received signal is low. And blockage. The blockage means that no signal is received in the user, by the user. So it's true that we have some problems, but we have some advantages to compensate, to counteract these effects, which is, for instance, the directional antenna gain. So at these frequencies, we could manage to have directive beams. So what we lose in path loss, we compensate it with higher antenna gains. Yeah? After that, we can see some of the problems, let's say in a visual way. How we manage? Imagine that these base stations use millimeter waves. Right now, you need with the current systems, with the current spectrum at 2 gigahertz or something like that, you needn't see have visual sight of the antenna in order to get connected. This is something that doesn't happen with millimeter waves. Imagine that you have this situation. This user is served by this one, by this one, by this one, with narrow beams, yeah? As the channel is changing, is varying, we could have a blockage here. So the network should be smart enough, should be self-organized enough in order to change and start transmitting from another base station. This is something which is challenging, and probably we'll need from the assistance of another node B, a macro base station, because these are small cells, low power nodes located in lamps, in traffic lights, etc. So the assistance of a macro base station will be required in order to do this. Yeah, this is mobility management, yeah, and the soft cell concept. There's another problem, for instance, which is visually easy to understand, which is the beam tracking. If this user, for instance, is here and starts moving, this base station should be able to steer the beam in order to follow the movement of this user. Because as beams are very narrow, we could lose the signal. This is why if this user moves, the beam should follow, should track the movement. Yeah? And this is obviously possible thanks to MIMO in millimeter waves. But it's also true that for several reasons, MIMO in millimeter waves, there's a good point for that, which is as you increase the band or the frequency, the size of the antennas is decreased, so perfect, because we can put more antennas together. We could densify the MIMO in the same space because antennas are smaller, but there are some other problems it's not important to mention right now, but they have problems with the conversion analog digital. Yeah. So this is, let's say, the new spectrum. But at the same time, as we are looking for a spectrum, we are desperate to find new spectrum. There's another concept which is pushed, let's say, which is posed by Qualcomm mainly. There are some industry partners which are pushing for it, but probably the most important one is Qualcomm, the American industry, probably one of the pioneering companies in the world, which is pushing for the following thing. Like, if we have, for instance, these bands are for Wi-Fi. What we have for wireless LAN, Wi-Fi, what we have at home, our router, yeah? Our routers, our wireless Wi-Fi routers use this frequency or this one, doesn't matter. This one is much more crowded, so a lot of routers use this frequency, but there are less routers that use this one, this band. These bands are free, so everybody can use it if certain rules are followed. Rules are, for instance, not using the band for more than a particular time, and apart from that, not transmitting more power than a maximum level, in order to, let's say, to allow the coexistence. So, taking this into account, in release 13 of 3GPP, so the standardization body, they suggested reusing these bands. Basically, the 5 gigahertz, because let's say it's less crowded, yeah, it's less used. So they decided to propose an LTE, so a 4G system that operates on these bands as they would do, for instance, as a wireless LAN, a Wi-Fi node would do. This has something good and something bad. For instance, for the operator, the thing is that he never knows when this band will be available, because this band will be shared with other nodes. So if the network operator wants to deliver a particular quality of experience, quality of service, I don't care, this band will not be so appropriate. In these bands, there are some rules that must be followed, and one of these is the listen before talk concept. It means that any user, any base station, before transmitting anything into this band, what it has to do is just listen the channel to see if there's somebody transmitting. If there's nobody transmitting, the node can transmit. If not, it should elapse the transmission. Yeah. So this is the LAAA system, and it's being standardized in 3GPP. But at the same time, there were some companies, Qualcomm in this case, in the States, that they wanted to, let's say, to put into the market let's say a product, a commercial product on these bands for LTE. So they designed this LTE-U, which means LTE unlicensed, based on some previous releases, where in fact the main difference with this previous one is that they do not respect this, listen before talk. This happens because regulations in the USA are completely different from the European ones. European ones are more restrictive in this sense. So basically these devices could not be used in Europe, but in the States. This is why Qualcomm and others just proposed, let's say, a proprietary standard to use in some countries, but if they want to operate with these kind of standards here in Europe and some other places like Japan, etc., they will have to go for this standard. Yeah? And there's even another solution also proposed by Qualcomm, but to be honest, I think it will not be that successful, where they say, okay, we work together, because in these two standards, what they use these bands as a complementary spectrum. Here, for instance, they have a commercial device, a commercial node that uses that just operates only in this band. So it would be something similar, following the 4th generation rules, but it would be something similar to wireless LAN, to Wi-Fi. Yeah, I don't think this will succeed, but okay. So the problem on these kind of bands is the coexistence with other standards like Wi-Fi, Bluetooth, etc., because all of them use the same bands. So although 3GPP consortium or standardization body insists that it is possible, the coexistence of LTE and these other standards, these other technologies on the same band, there are some studies, for instance, it's worth reading this one from 2 research engineers from Google, where they said literally that it was not possible to share the band in a fair way. So this is something that, let's say, they will have to fight, they will have to push a lot in order to implement this, for instance, in places like in Europe. Yeah. So we talk about the performance, we talk about the spectrum, and finally the densification of the network. Networks will be completely different. Yeah? As you remember, we want to increase the number of base stations 10 times. Yeah? So basically, networks will be like this. There will be some base stations, some macro base stations, like the ones we have in the rooftop, and then there will be different base stations, smaller, let's say, closer to the customers, let's say in lamps, in traffic lights, etc., that could be femtocells, picocells, etc. In general, the general term, small cells. They will have lower power, and they will be used in order to provide capacity to users around. Yeah? The interesting thing is that there are some studies. This one was the seminal study, the one that settled or established the basis of this, that they say, for instance, here what we have is red points are, let's say, macro base station locations, and the others, the blue ones, are small cells. Notice that this is the, let's say, this is the visual effect that we would see if we were on top of a roof, let's say, or we fly over our cities, let's say, and we see the aspect of of the network. Know that, for instance, here, if we zoom into that image, we will see that these lines are the coverage areas. I mean, for instance, all users located in this region will be connected to this. All users in this location will be connected to this At the same time, all users within this region will be connected to this one, yeah, as you see, because why it's like that? Red points are macro base stations, so they transmit higher power, and the others are low power nodes. And this is the aspect actually our network will have in the future, and actually this is the aspect that is starting to have our network nowadays. So the interesting work here, this work, which was, let's say, the seminal one, is that no matter how tiers, no matter how base stations you include in the network, because in the end, if they have the same signal to interference noise ratio target, including more base station will not lead to a higher outage. It means the loss of coverage. In general, this means that users are not affected by interference even if you include a lot of base stations, different tiers. Yeah, interference grows as signal strength does. Yeah, so based on this, the solution was clear. I mean, the network, the radio access network, should be densified. And let's see, pros, which are the positive points. The capacity per area unit will be increased for sure, by doing that. But there are some cons. Negative points, or let's say challenges. The network should self-organize. As you see, the network is absolutely, let's say it's not regular. So the network should be able, on its own, to detect the situations and organize on the fly. Backhauling problem. Notice that I put this, just included this figure because these are, let's say, raindrops. Imagine that each one of these raindrops are base stations. And let's say these waves are the signal. Note that as we have better base stations deployed everywhere, what we have is a scenario where here we concentrate a lot of capacity, a lot of megabits per second. All megabits per second that are served by this cell are here. The same here, the same here, the same here. And we have to forward this data to the core network. The forwarding of this data must be done through the backhaul. The backhaul is the connection that, let's say that, yeah, the connection that connects the base station with the core network in a single hop or multi-hop communication. And obviously, the other huge problem is the cost increase. Obviously, as we include more nodes in the radio access network, the network operators have to pay for that. And obviously, this is a real problem, because network operators, apart from delivering really good services, they want to earn money. Yeah? So this is a real problem. And I will just mention one thing for each of these three possibilities, or some of them actually. Oh no, I know, sorry, okay. Then, this is the densification, and I go, actually, it's two more. One of the challenges that we had at the beginning was the number of devices. And I just want to show you this chart, also from Ericsson Mobility Report, the one that I showed you, where they have the expectation, actual values and expectation of the device, of the number of devices worldwide connected to the network. And it's really interesting because, note, mobile phones, do you see the trend? There's an increasing trend in the mobile phones connected to the network, but it's not that slopey. Yeah? On the other side, you have PC and laptops, the blue one. Okay, it's increasing, it will increase in time, but it's not that much, actually. And then you have two types of devices that, let's say, in a percentage, speaking about percentage, will increase a lot, which are consumer electronics, so all these devices at home that will be connected to the network, the washing machine, whatever, the vacuum machine, anyway, which is the purple one, and finally, machine-to-machine communications, the red one, the green one. These machine-to-machine communications are everything. When we talk about Internet of Things, it means getting connected, I don't know, what I said at the beginning, like sensors, etc., etc. We talk about this type of communications. And there's something which is interesting, that current networks are not designed to serve this kind of traffic. They are mainly designed to serve this traffic, this kind of traffic. So as you can see, the problem is that in the future, the traffic which is going to grow consistently is not this one, which is, let's say, the objective of the current network, but this one, which was not important when the current network was designed. So this implies that we will have to do something in order to improve how network serves that traffic in order to meet the demands. And just something about how they are going to do it. Currently, users have to get connected to the network through an access that can be contention-free or contention-based. Contention-free is used only for reserved services, so it's not that common. For instance, for handover, in order not to lose the connection, etc. But most accesses are done in a contention-based manner. What happens with this MTC, or let's say the machine-type communications? These devices, sensors, etc., normally have no power supply, so they have to save energy for sure. They have to save energy if they want to extend their lifetime. So basically, it's important to disconnect these users when they have no data to transmit. This is a problem with the current network, because the network is thought for devices that are always connected. So the problem with contention-based random access is that all these devices, sensors, etc., when they want to get connected to the network, they have to reconnect every single time. Yeah. So the energy they saved by being asleep during a long time, they waste it just in order to access. And there's another problem, that the access, this random access, the resources the network devotes for the access are limited. Why? Basically because the resources you use for the access are not used for transmitting data. So networks or network operators try to minimize the number, let's say the resources devoted to access, in order to maximize the resources for data, for transmissions, etc., for services. So basically, what they have is that they access randomly in particular time slots, and they select one out of 64 orthogonal preambles, and two users only collide in the access of the network if they use the same time slot, and the same orthogonal preamble. This could seem, let's say, not that much. I mean, the probability of collision is not that high. But take into account something, I go backward, that we are talking about 26 billion, okay, let's say in Spanish would be 26,000, yeah? It's like, for English speakers, we have to subtract 3 zeros, eh? We are around this amount we are expecting this amount of users connected. So this will not suffice. We will have to do something. Why? Because in the end, the current situation poses some trade-offs. It's capacity versus access opportunities. If we want more users to get connected, more devices to get connected, we will lose capacity. Contention-based versus contention-free. If we want, because we could consider, okay, we could devote more resources to contention-free, so that those users, every time they want to get connected, they will not collide. But the problem is that resources are limited. So if we devote these resources for contention-free access, we will have to subtract them from contention-based access. So we have here a trade-off, and we have another trade-off, which is the machine-type communications access versus the human-type communications. So the problem is that if we have a lot of devices, sensors, etc., actuators, etc., around, the problem is that they could block, they could devastate the access of human-type communication, so of people trying to get connected with their mobile phone. So here we have a problem. And this is one of the most important problems to be solved for the next generation. And there are solutions. There are solutions which are, let's say, trying to make more efficient the access. So as we access the network, let's say, we take advantage, we benefit from that slot, and we send the data. We could also prioritize different types of devices. So those devices, for instance, with more, let's say, power supply constraints could be allocated at the beginning, or with more, let's say, strict constraints in terms of delay, etc., etc. And as well, a division, let's say, some resources for human-type communications and some other for machine-type communications. But the problem persists because, I mean, we can solve something, but in the end, the resources are limited. So what they decided is to design, almost from the scratch, a new radio access technology. They are trying to implement a radio access technology in order to support, to service the users, the machine-type communication, so Internet of Things, in a native way. So a radio access technology aimed to serve these kind of users. This is what happened, if you remember, with the previous generations and the third one, for instance. They were they were focused on voice communications, and then there was a shift to data communication. Here is the same. The thing is that right now, the standard is starting to introduce new features in order to solve this. The problem of energy saving and the problem of the cost of the devices. Yeah, because it's important that these devices that will be a lot, yeah, have to be cheap. Yeah, so basically they started to include some features in the standard, but however, it's not enough. It's not enough. So at the moment, there are different things that are, let's say, focused by the research community. For instance, reusing some bands, for instance, GSM bands. I mean, the number, let's say, the voice traffic, as we saw in the previous slide, does not grow as could be expected. And apart from that, the coverage of the third generation systems is almost 100% for instance, in Western Europe. Yeah. So basically, what they consider is, why not, if we implement this new radio access technology by refarming the GSM bands. So we take out GSM bands because we can serve voice through UMTS, and we put there a new radio access technology. By doing that, network operators will save money because they will only have to change only part of the hardware in the already deployed base stations, and at the same time they will use some new frequencies, which are interesting. Okay, but this is, let's say, a temporal solution, but there are, or let's say, a solution that comes together with this development of a new standard, a new radio access technology within the 5G standard. Yeah, and this would be, there are some initiatives, some interesting, let's say, companies, alliances like Sigfox, like LoRa, this is a French company. LoRa is an alliance, an international alliance, but also established in France because they are, let's say, the pioneering works in these kind of networks are done in France. Null, OnRAM, this is from Huawei, Weightless, there are some of them, and more of them will come. Yeah? So the thing is, developing a new radio access technology and natively include it into the standard. So probably this is a research field that will attract will capture the interest of the research community for sure, or at least the network operators for sure during the next few years. Yeah. And finally, the latency. The latency is one of the key aspects, the delay, one of the key aspects of the new services. New services are expected. For instance, gaming. If you want to play with somebody using your mobile phone, you want to have, let's say, a short delay, a very short delay, because it's interactive. This is something that currently in our networks we have approximately a round trip latency of 15 milliseconds. So the time that we need in order to send something to the other and receive back the answer, let's say, it's 15 milliseconds. This is too much. This is too much for these kind of applications. So the latency will have to be reduced. And it's not that easy, because it affects not only the access interface, but also the network itself. And note something, in current networks, let's say the subframe is 1 millisecond. So it's, at the moment, it's impossible to have less than 1 millisecond to get data from the user to the base station. And we are asking, we need for the future 1 millisecond go and back. So it's one of the challenges. And around this latency problem and these new services, a new concept arose. I don't know how successful, at the moment it is successful, I don't know what will happen in the future, but it's the tactile internet. This is something that for sure you will see. And this is one of the, let's say, some gurus in the field, like Professor Petweiss and Professor Dochler. Yeah, these two professors, which are well known by you, proposed a new concept a couple of years ago, tactile internet. And actually they proposed this for the first time here in Barcelona in the Mobile World Congress. Yeah? And they proposed something which is defined by the ITU as extremely low latency in combination with high availability, reliability, and security. Actually, they were initially thinking, for instance, about having, let's say, remote robotic control through the internet, through the cellular network. And in order to do that, you need for sure those, let's say, low latencies. So around this concept, there's a lot of work to do in many different fields, because it has to do with access technology, the network, how the infrastructure of the network is done, how services are delivered. So it's a new field. So probably this will be a field that for the few years, or at least in the next future, and in the near future, it will gain importance. And actually, it is gaining importance at the moment. Yeah. And finally, we had the problem of energy consumption and the problem of the cost, yeah? And I'm finishing. So, sorry, the cost, yeah. The cost has to do with the electric bill that has to be paid by the network operator. Having a base station transmitting, it means, having a base station transmitting means wasting or consuming some energy, and this has to be paid. Yeah, so it's a problem for the network operator. And at the same time, as I mentioned, the densification of the radio access network, so in deploying more and more nodes, causes an increase in the capital expenditure. So in the money they need to invest in order to have to get the network deployed, and at the same time in maintaining this network, so the operational expenditure. So these are the facts. And what happens with the electric bill? Some data. According to a Nokia work from this year, what they say is that 0.5% of the worldwide electrical energy consumption is used by ICT industry. So basically, our computers, basically not our computers, actually our network, cellular network, the mobile phone, so the system that we need in order to make our mobile phone working, consumes 0.5% of the total energy consumed in the world, which is a huge amount, yeah? Apart from that, they say that this energy, this electric bill, is basically means 10 to 15% of the total operational expenditures of the network operators. So basically, the maintenance or the transmission or the maintenance of all the network, if you take that cost, 10 to 15% is caused by the electric bill. And in developed countries, it could reach up to 50%. So there's a real interest for the network operators, apart from environment issues, to cut down this consumption. And in the recent years, in order to see how it's evolving, in the recent years, this consumption grew with this percentage, from 15 to 35%. So it's something that in order to meet the demand, in order to be able to serve the users, the energy consumption grows. So this is a problem that has to be addressed by the network operators. At the same time, the densification of the network, there are some interesting things that could be done. How to cut down the cost of deploying a network? The first concept is simple. Basically, sharing the network with other operators. If the cost of deploying a network by each user on its own, by each network operator on its own is very expensive, why not doing among different network operators and sharing that network sharing. And at the same time, the nodes that they deploy around the scenarios, I mean, in the network, should be cheaper. Yeah. So based on this, I just pose, just to finish, the open research fields that should be addressed in these two issues. For instance, for the energy consumption, small cells. So the inclusion, the evolution of cells into small cells, low power nodes. Yeah. At the same time, there must be an improvement of efficiency. This is something hardware related. So basically, bandwidth processing, etc. The operation of the network should be related to energy consumption and to the energy consumption. So the network should make the decisions according to what is more beneficial in terms of energy consumption, not only in terms of traffic. And this is something that has been studied here and CTDC and UPC. There's a girl who got the PhD on this. Other strategies, turning on and off some base stations. And finally, including the energy harvesting technologies. Basically, what they are saying is that if we have the network absolutely densified, so if we have networks deployed here and there, probably it's more optimal to have some kind of energy harvesting in the nodes. So getting the energy where it is going to be used. This is something that, let's say, it's just at the beginning, but this will take more and more importance in the future. So probably we will have some base stations with a solar panel, or we will have a base station with other technologies in order to get energy and reduce the bill. Yeah? We will consume energy, but at the same time, we will harvest energy. So we will be more, let's say, clean. And this is for the energy consumption. And finally, for the cost. How are we going to reduce the cost of the deployment? Basically, this is something which is well explained in the project SESAM, which is a 5G PPP project based on this. What they say is, okay, if we want to reduce the cost of the network, we should deploy cheaper nodes. In order to do that, it means that we have to take functionalities from these nodes, from the base stations, and put it somewhere else. Because, I mean, if we want a node to be smart, if we want a node to do a lot of things, it will be expensive. So if we take functionalities and we take it out from the node and we bring it somewhere else, we could reduce the cost of the deployment. And actually, here is where cloud radio access network this concept appear. Basically, they consider cheaper nodes, remote radio heads, like this, and a centralized management. So basically, they connect to a central unit in the cloud. They connect through fiber optics, the cloud, the baseband units, and the remote radio units or the remote radio heads. By doing this, there are, let's say, two important things. I think I have something here, yeah. There are two important things. On the one hand, we reduce the cost, but on the other hand, at the same time, what we do is that we increase, we just go for a centralized management, and so we increase the efficiency in the usage of the resources. It's also true that we have a negative impact, which is that laying the fiber optics, it's very expensive. So it will not be that easy to have all radio units connected through fiber optics. So probably for some time we will have a hybrid situation where we have some nodes connected through wireless links, and so with more, let's say, layers, with more functionalities implemented there, and we will have some others with connected with fiber optics, and let's say only with layer 1 and the baseband unit in the cloud. Yeah. So basically, what we are saying is that if they want to reduce the cost, they will have to rethink completely the network. So the network from the operator point of view will never be the same. It will change during the near future. So okay, in order to do that, here I just included a slide. I just included a chart where we can see that this situation where to locate, let's say, the functionalities, the intelligence of the network, or the different layers, the functional layers, will have an impact. The more layers we include in the nodes, the more expensive they will be. So the cost will be higher, and the RF improvements will be less, and the other way around. Yeah. So more or less, this is I just tried to give an overview of the whole network. So after that, I would like you to understand that the networks, I mean, future networks will be completely different, and the way we get connected to the network will be different as well. So be ready for a lot of changes. And thank you. I don't know if there's any question. I don't know. We spoke better. Yeah. Okay. Thank you.